Hi, everyone. Welcome to SigOpt Summit, and welcome to my session, Democratizing End-to-End Recommendation System. My name is Zhang. I'm from Intel AI and Analytics team. Currently, we are focused on democratizing end-to-end recommendation system on commodity hardware to make it scale to better scale and easy to use. Let's take a look on the agenda today. So we will talk a little bit about what is the recommendation system, what is the architecture of a recommendation system, and then we will start in to look at why we need to end-to-end AI democratization, which part we can try to work to democratize it. After that, we will choose several typical recommendation system workload as an example, as a prototype to showcase what we have been accomplished so far. And then we will showcase how we use SigOpt to scale out the end-to-end recommendation system and wrap it up with a summary and the next steps. So what is the recommendation system? Recommendation system is a software that elicits the interest and the preference of individual customers and make recommendations accordingly. It is usually to make recommendations for your request like what book I should buy and what is the best place for my family to visit during our vacation. It helps to match user with different items to ease the information overload and assist sales. Recommendation system has been developed steadily over the past few years, especially in multiple areas like retail, e-commerce, healthcare, transportation, etc. It was said that recommendation system account for like 35% of the Amazon's revenue, and a 1% improvement can be translated into billions of dollars revenue. Let's take a close look on different recommendation system design, starting with the personalized recommendation system. Take the Amazon bookstore, for example. When you click on the Your Recommendations link on Amazon.com, it will lead to the user page full of products recommended just for you. The personalized recommendation system is based on the user profile and the contextual parameters like gender, age, and favorite selections. So the second type is the collaborative recommendation, which is leveraging the community data. For example, the taste information from many users to provide predicts, like tell me what is the most popular thing among my peers. It collects and analyzes users' behavioral information like their feedback, rating, preferences, and activities, and then explores the similarities between those different users and make the suitable recommendation. The content-based recommendation works like show me show me more like the same what I have lacked. It is based on the description of the item, a profile of the user's taste to recommend items similar to those which a given user has linked in the item rich list, which is suitable for situations where there is some non-data on the items. Knowledge-based recommendation. It is based on explicit data like about the item assortment, user preference, and the recommendation criteria. It works like tell me what fits based on my need. For example, when you try to buy a car, you may have a specific request on the car color. So the strength of the knowledge-based recommendation is the non-existence of the co-starter problem. The last one is the hybrid one, where it's a combination of various inputs and the composition of different mechanisms. Most recommendation systems today now use a hybrid approach. It's combining the collaborative filtering, content-based filtering, and other approaches. With this, let's take a look on the recommendation system architecture. So a typical recommendation system can be divided to two different parts today. The first part is the data and info part, where you're collecting the data and processing it and doing feature engineering, transform the data to some format that the deep learning framework can be processed. Based on different use scenario, you can use the real-time data processing, streaming data processing, or batch data processing. And you can use rich feature engineering technologies to generate the user info, item info, and content info. After that, you will feed those features to the training framework. The model and the algorithm part is where you build models and trying to um, make the model for serving. Usually, it will both include offline training and online model update. You perform A/B test to predict the recommended items in a short time. Is pretty challenging. So this serving phase usually involves recall, ranking, and re-ranking. The recall tries to generate a small set of items that the user might be interested based on the user profile or the product's characteristics. Then it sends it to the ranking part. This phase needs to be extremely fast. And for the ranking phase, it's the most critical part of the recommendation system. It needs to be very accurate. The more accurate your model, the more potential revenues you can generate, or the more business impact it can be made. So, however, there are a lot of challenges with the recommendation systems. The first and foremost one is there are huge amount of data. The recommendation system are often trained on large data set, often at a TB and petabyte scale, so which requires a large cluster to store and processing the data. And usually it introduces multiple challenges like a slow data movement and the data movement, especially the data movement will run into separate data processing and a training cluster. The second part is the data processing. So data sets need to be loaded, cleaned, and processed, and then transformed to a suitable format. So you need various of different data processing technology. You need a scalable infrastructure to run the data processing. After that, the feature engineering will create a numerous set of features need to be created and tested. You need to employ a lot of different feature engineering technologies like BCA encoding, etc. Model and algorithm. People usually create complex models and algorithms. This definitely creates an entry barrier for citizen data scientists because it's so complex and requires a deep technical expertise for the complex models. Even with all these different parts, you still need a repeated experiment because there's no way you can get the design model in one single experiment. So the ETL, feature engineering, and the training evaluation process need to be repeated for many times and with many model architectures. So it also needs periodical update to maintain the high accuracy. With all of this, the category feature of the recommendation system usually requires embedding and requires a large amount of memory. So the lookup part is really bandwidth intensive. This creates some challenges for the cluster. And with this extremely high computing power, it usually requires distributed training, which makes the scalability critical. Let's take a look on what is the goal of end-to-end AI democratization and what we can do. So the goal of end-to-end AI democratization is trying to make AI accessible and affordable for everyone. There are two aspects of this goal. The first one is the software side. Currently, AI is restricted to data scientists and data analysts who are specifically trained in AI. We want to expand it to citizen data science users. And on the hardware side, today AI requires high-end hardware, which like expensive GPUs and multiple socket CPU cluster. We want to make it scalable to community hardware. On what to be democratized part, the first and foremost thing is the data access and the quality part, which is basically the data platform. So the data platform is where you need to make the data access easier and simpler and faster. The common way is to democratize the data management platform. We build a platform that simplifies the data ingestion, the data management, the data warehouse, and data lakes, so that users can explore and visualize and process the data in a short time. Storage and compute platform are the foundation of the AI infrastructure that those workloads are running on. Usually, It might be cloud computing infrastructure that provide auto-scaling features to reduce their cost. It can be based on GPU and CPU. And we need to democratize the hardware, which means we want less scalable infrastructure running on commodity hardware that's not so expensive. And on the algorithm part, the user developers and the sharing of the AI and machine learning deep algorithms, we need to reduce the entry barrier, like automatic model searching, AutoML, to improve and meanwhile improve the explanation of the result. On the model development side, we want to select the most suitable models, and we need to democratize the end-to-end model development pieces. Um, and least, but not the last one is the marketplace. So where you want to access and reuse the other models. This part we need to democratize the use, exchange, and monetizing of the data, algorithms, models, and outcomes. With this, our goal here is pretty straightforward. We want to bring end-to-end AI existing commodity hardware through assistant AutoML to achieve the desired models with good enough performance, which means it's not targeting for the cases where you were seeking for the highest score, and thus requires a huge GPU cluster. And the second goal is we want to enable the previous few to run or week-long running deep learning models to be able to complete in hours in commodity hardware and maintain same or close performance. So with this, it makes AI more accessible for the citizen data scientist. And the last thing, we want to improve the citizen data scientist AI accessibility through enhanced AutoML with automated assistant intelligence suite. So with this, they do not need to have such kind of a deep knowledge on how to build the complex model. Our strategy is first to prototype with selected top model. Here we choose DRM, DIN, wet and deep, and optimize it from end-to-end perspective and reduce the end-to-end time to an accurate range. Then we try to identify the critical optimizations, the missing functions, and improvement new features. Now we build a scale-out democratizing solution with user-guided automation through parameterized models and SigOpt AutoML. Let's take a look on several examples. This picture actually shows the workload we have been tried and the performance speed up we have gained through end-to-end AI democratization. We were using wet and deep DIN and DRM models, for example. Here we can clearly see that significant speed up through end-to-end AI democratization. 100 times speed up, 17 times speed up, and 9.45 speed up for DRM, wet and deep, and DIN respectively. So the key optimizations, the first part is the data processing. We replace the previous single-threaded Python panels or NumPy data processing with scalable Spark data processing. The second part, we were using the inter-optimized training framework like IPX and inter-optimized TensorFlow. Then we try to reduce the model size. We're using lighter models, reduce the MLP layer, neural network layers, reduce the communication overhead on Ethernet. So it's not making communication an overhead. We're also trying to optimize the optimizers to converge faster with larger batch size. And we also improve the safe engineering like embedding and encoding. With this, I will give a quick introduction of several different individual phases. Like for data processing, for the DRM for the wet and deep data processing, we actually all using Spark here. So we comparing the left picture and the right picture. The left picture, NumPy is the original DRM NumPy based data processing. After each, because it's single-threaded, it can only fully utilize one call, regardless of how many calls you are running. So we change that to Spark, and then we scale it up to multiple Spark nodes. This leads to significant performance speed up. And then we try to improve the Spark usability. we developed a project called RecDP, Recommendation System Data Processing. It enhanced the data processing with Spark with a pluggable model based on the PySpark. And it's also provided easy to use API, like a categorified job and job. So you do not need to worry about how to write Spark code. They're also doing optimizations based on Spark, like a transparent join strategy, like inline Scala UDF functions, and also leveraging the inter-optimized native package, like the native SQL engine, to further improve Spark performance. This plugin model can be easily integrated to other end-to-end platforms. On the data connect side, there is a missing gap between the data processing and the training cluster. So here, we want a parallel data connector that can bridge the two. So with this, the training cluster can load the data from the data processing, the centralized, the distributed storage directly. It also needs some kind of advanced features like local caching to improve performance, and also support data promotion and flushing in case the local cache capacity is not enough. So PetStorm is actually an open source library that enables single or distributed training of deep learning from a multi-terabyte dataset in Parquet format. So based on PetStorm, we build a data connector. We enhance the PetStorm through with several enhancements. The first thing is the raw data loader extension to replace the DRM binary data loader. The second thing is we implemented a method to ensure the consistent batch set around across different ranks, so the train part will not fail. With this enhancement and the PetStorm, we can doing training with large data set directly without a manual split or combination with the data set. On the training side, this is the wide and deep model example. It shows how those different optimizations improve the performance. So the inter-optimized TensorFlow, we apply the OpenMP and KMP optimization for CPU. And after that, we try distributed training using Horrorboard. It scales to 1 node to 4 node, which delivers 1.9 speed up. And then we try to reduce the sparse embedding size and also the hidden unit size. This delivered a 1.14 speed up. We also enabled early stop because compared with GPU solution, CPU can kind of deliver the same score with even smaller number of experiments. So this delivered a 4 times speed up. Also, we enabled data loader prefetch and tune data loader thread number and buff size to improve the input pipeline efficiency. And hypermeter tuning like learning rate and other optimization like SigOpt eventually improve the training time by 58 times. To sum it up, those optimizations can be categorized to data processing optimization, feature engineering optimization, and the training optimization. Data processing part is parallel data processing replaces the previous single-threaded Python or Pandas data processing. Feature engineering side, we need the embedding optimization, encoding optimization. On the training side, we need to figure out how to chain the optimized training framework and the scale out training, optimize the stuff together. So we need a better way to scale this democratization work out. Then we start to evaluate how can we leverage SigOpt to do the scale out thing. SigOpt is a model development platform, make it easier to track runs, visualize trainings, and scale hypermeter optimizations for any type of models built with any libraries and on any infrastructure. So it's also an experimentation platform. What we're trying to do here is we want to leverage SigOpt for hypermeter tuning to keep track of the experiments for AutoML. Then we can provide a customized, parameterized models through SigOpt YAML configuration files for advanced optimization. So then we can integrate the SigOpt with RecDP and other frameworks. Let's take a a close look on what we have done. The first thing is we developed a new component called Smart Democratizing Advisor, SDA, which is a user-guided tool to facilitate the SigOpt recipe generation based on the expert data scientist input. So the input include multi-part like a dataset, feature shape, model, and parameters. The output will be a single YAML file, including the features, the training, related models, etc. So SDA will create an experiment and explore best models automatically. With SDA, we can start doing democratization with SigOpt AutoML. So the phase works like SDA generated the parameterized SigOpt YAML file based on expert data scientist input, and then SigOpt orchestrate and visualize the experiment. So SDA will kick off one experiment and leverage SigOpt for orchestration, visualization. The integrated model compressor will enrich the compressing capabilities. It runs through the optimization loop to get the suggestion from SigOpt, evaluate the metrics, and report observations. Then we can get the best parameter group, visualize it, and analyze it. And outside of the SDA and SigOpt, we have another end-to-end framework that can integrate SDA-powered SigOpt AutoML with the RACDP and the model serving side. So it works pretty straightforward. We organize the configuration files, the SDA in a single project. It will kick off SDA will kick off the SigOpt AutoML through a Python script directly. And with this, let's take a close look on the detailed example of one recipe file. This is one example of the parameterized SigOpt YAML file. It basically provides manually tuning parameters when you're creating SigOpt experiment. So there are model parameters like the network layer size, the embedding feature size, the Jian unit size, etc. And there are also training-related parameters like learning rate, warm-up steps, etc. So the user can also choose to generate parameters directly if they have some kind of insight or knowledge, or if they have their own different preference. The SigOpt optimization loop will wrap up the model training process in SigOpt, and then the budget can be reduced through the parameter recipes. Imagine that previously it may take like 40 experiments to complete the process to find the desired model, but now with these parameterized recipes, it might only take like 10 or even less number of experiments. And meanwhile, we also leverage the SigOpt advanced features like multi-metric optimization, metric threshold to further improve the AutoML efficiency. So here is what SigOpt-based AutoML can achieve so far. The left picture is the AutoML training speed up. The left picture is the model performance. So our conclusion so far is SDA-powered SigOpt delivered excellent result. On the performance side, it delivered a similar performance, the same MAP value for wet and deep model, and the same AUC for DRM model. And on the timing side, it can achieve even better performance compared with the previous manual optimized models. More importantly, it can transform the heavy lifting manual tuning optimizations into AutoML. So this will eliminate the entry barrier for citizen data scientists. The training time, here in the left picture, we are using the best value or the best observation experiments. The training time will reduce like 3.18x for one deep and 1.07x for DRM. Not only that, SigOpt also provided an easy to use and understand UI to help you to compare the models, to use and understand the models, and explain the result. So here is the example of the parallel coordinates, which is a graph that shows the high-level patterns in the data over many dimensions. Let's take a close look on this. The vertical axis graph with the metrics and parameters so that the larger DNA unit and the smaller learning rate, we can get higher MAP. So users can change the parameter range and rerun the optimization loop to find optimal parameters. The horizontal axis is ordered by the parameter importance. As SigOpt optimization proceeds, the most important parameter will be limited in a range, so it makes the user able to freeze the parameters and reduce the number of parameters. With the matrix threshold, SigOpt can focus on some sampling and a more promising parameter region. SigOpt auto optimization. With SigOpt auto optimization, we can get optimal parameters with higher MAP and lower the training time compared with the manual tuned parameters. The last part is we want to take a close look on how SigOpt achieved this. There were two important features we tried so far: multi-matrix and matrix threshold. The performance, before we enable the two features, we actually noticed slightly performance regression with single metric SigOpt AutoML. That's what have been sold from the left picture. So the menu optimized the models, the best time we normalize it to if we set that to 1, we noticed the 0.22x regression for the SigOpt AutoML. Then we talk with the SigOpt team and we enabled the multi-metrics and the threshold. It bring the performance back. And for the reason is it will consider multiple competing metrics like which might have optimal values for different parameters. It's trying to maximize the model performance and minimize the training time. So thus it can reduce the number of experiments to get the best models. And meanwhile, there will be significant training time reduction compared with the without multi-metrics and matrix threshold. So if we take a look on the graph, this is a detailed explanation of how multi-metrics and matrix threshold helped. From the wet and deep single metrics, it's clear that SigOpt and AutoML can guarantee MAP value increase among trials, but it requires 40 plus trials. And with the multi-metrics, we can get a balance between the training time and MAP values. And once we added the matrix threshold, we can better control the training time and the performance, and thus significantly reduce the number of experimenters and improve the experiments that deliver the same AUC but with much smaller time. So the same story for DLM. With those two features, the number of experiments delivered the desired AUC increased even with shorter time. So this is the key where SigOpt helps. To wrap it up, end-to-end AI democratization brings the AI to community hardware through assistant AutoML, improved AI accessibility, delivered good enough performance with lower TCO. Our prototype on DRM DIE wet and deep so that it can deliver a significant improvement in end-to-end training time with same performance. The major democratization techniques, including parallel data processing, scaled training, lighter models, and high parameter tuning. Those optimizations can be scaled out through enhanced data processing and assistant SigOpt AutoML. SigOpt with SDA delivered a similar result as manual optimization and make it easier to scale out with the democratized models workload. So for the next, we will extend the democratization to more models and datasets. I want to thank for the contribution from my team members, Chendi, Bing, and Tao. Thanks. That's all for the session.